Hello friends, welcome to SS and CD class. So in the previous class we have seen architecture of SIC machine. In this class we will see architecture of SIC XE machine. Again there are six or seven concepts we have to discuss here. In that one, first one is memory. So memory in SIC XE machine is 2 to the power 20 bytes, that is nothing but 10,48,576 bytes, or else we can call it as 1 MB of memory, or else simply we can remember it just as 2 to the power 20 bytes, because in SIC we remembered that that SIC machine has 2 to the power 15 bytes of memory. So here it is SIC XC machine has 2 to the power 20 bytes of memory. So memory structure is same as that of SIC, that is 8-bit bytes here also, and words, address of words, these all things whatever we have studied in SIC, the same thing is here also. It means that SIC XC memory is also 8-bit bytes, and consecutive 3 bytes will form a word, and each word will be addressed or accessed with the help of lowest numbered bytes. The same things are repeated here also. Then maximum available memory is 1 MB here, that is nothing but 2 to the power 20 bytes. But in SIC this memory was 2 to the power 15 bytes, and because of this increase of this memory, instruction formats as well as addressing modes will be also changed in SIC XC machine. So if you remember, in SIC there was only one instruction format. It means that all instructions what we use in a SIC machine to write the assembly programs, those all instructions that we use in SIC machine are of same format or same syntax, that was a 24 bits format. So first 8 bits are for opcode, and 1 bit for flag bit X, and last 15 bits were for address field. So now in SIC there are four instruction formats are there. We will discuss them one by one later. And again there are many number of addressing modes are available in SIC XC, whereas in SIC there were only two addressing modes. One was indexed addressing mode, and another one was direct addressing mode. Okay, so direct addressing mode and indexed addressing mode were there in SIC, but here more than two addressing modes we will study in this SIC XC. So this, because of increase of this memory, these instruction formats are also different, and addressing modes are also different than that of SIC machine. Now come to this resistors. Resistors is nothing but it is also one storage device, which is the smallest storage device. Okay, so in SIC there were 5 resistors, A, X, L, PC and SW. But in SIC XE, in addition to those 5 resistors, SIC XE has again 4 resistors. So whenever we write architecture of SIC XC machine, we cannot write only these 4 resistors. So it means that SIC has a total 9 resistors, because the SIC machine whatever the resistors it had, it was A, X, L, PC and SW. In addition to these 5 resistors, SIC XC has these 4 extra resistors. So total SIC XC machine has 9 resistors. So SIC XC also has A, X, L, PC and SW, and the same numbers and same special uses are same here. But in addition to these 5 resistors, what are the extra resistors we will see now. The mnemonics are B, S, T, F. It means B is nothing but base resistor, S is general working resistor or general purpose resistor, T is also general purpose resistor or general working resistor, F is a floating point accumulator register. So B is base register which is used for addressing and its number is 3. S as well as T are general purpose or general working registers and they don't have any special use. Their number is 4. So if they don't have any special use, then we can use this S and T register for any general purpose working during the writing during the execution of our program, assembly level program, or while writing the programs. It means that the main purpose of these registers are to store the small amount of data. So if you want to store any small amount of data temporarily, we can use these two general purpose registers S and T, and the number for T register is 5, and last register is F, that is called as floating point accumulator register, and its length is 48 bits. See, so previous registers, whatever we have seen in SIC, those all registers were 24 bits length, but this F is of 48 bits length and its number is 6. These numbers are very, very important to solve the problems in next classes. So next concept is data formats. So already we have seen in SIC that we can store integer type of values in SIC as well as we can store character type of values, but we cannot store floating point values because there were no any floating point hardware in SIC machine. But in integers only we could store negative values also by using 2's complement. So now let us see in SICXC what type of values we can store here, what type of data we can store here. Okay, so SICXC provides the same data formats as this standard version. In addition, there is a 48-bit floating point data type with the following format. The data format is this one for floating point data. So first 1 bit is for S bit, and 11 bits for exponent, and 36 bits for fraction. See here, this fraction describes or explains a value between 0 and 1. It means that it is a binary point which is immediately before the high order bit. Okay, so for normalized floating point numbers, this high order bit of this fraction should be 1, and this high order bit is also called as most significant bit, that is MSB. Okay, then exponent describes an unsigned binary number between 0 and 2047. The value of this exponent will be in between 0 and 2047, and if this exponent has value e and this fraction has value f, then the absolute value of this number is represented as f into 2 to the power e minus 1024. Okay, you just remember this formula, that's all. So here main thing is the data formats are both integers, both in a negative as well as positive, as well as we can store here characters also. Along with these things we can store floating point values also, and this data type floating point data we can store in this format. So first bit is yes, 11 bits are for exponent and 36 bits for fraction. So total 48 bits are there to represent this floating point data. Okay, in that one fraction describes the value between 0 and 1, and exponents describes the value in between 0 and 2047, and next is the S bit is called as sign bit. So sign of this floating point number is indicated by the value S. If the value of S bit is 0, then the floating point value will be positive value, and if the S value is 1, then the floating point value will be negative. So this the value is 0 is represented by setting all bits sign, exponent and fraction to 0. The total complete if that entire digits of that floating point value. If it is 0, it means here I have written 0.000. If it is like this, then if sign bit is also 0 and exponent is also 0 and fraction is also 0, then we have to set these all three bits, all three field bits to 0. So when it is, if the floating point value if itself is a 0. And instruction formats, as I already told, because of the increase of memory in SICXC, there are four different instruction formats are there. Whatever the instructions we write in assembly level program in SICXC machine, those instructions are four different types. So but in SIC, there was only one instruction format was there. All instructions are in that format only. First 8 bits were for opcode, and 1 bit for flag bit, and last 15 bits for address field. But here there are four different instruction formats are there. Let us see one by one. The larger memory is available on SICXC because already we have seen this one. 2 to the power 20 bytes are available on SIC. Therefore this address will not be fit into this 15 bit field, 15 bit address field. So what we have already seen in SIC. Therefore this instruction format of SIC is not same for this SIC XE. So two possible options are there. What we can do here, either we can extend the address field from 15 to 20 bits. Okay, so because in SIC only 15 bits of address field was there, now we can extend it up to 20 bits. Or else second option is we can use the same form of relative addressing, or we can use some relative addressing modes. These relative addressing modes usually we will use in format number 3. Okay, and we can extend this address field, 15 bits of address field, in format number 4. We will see this for format 3 and format 4. So we can extend the 15 bits of address to 20 bits only when we use format number 4, and we can use some relative addressing modes when we use format number 3. We will see these formats. Okay, so SICXC also provides some instructions that do not use memory at all. Those formats are format number 1 and format number 2. See, this SICXC machine has some instructions which do not want or which do not use memory at all. It means that they may use only registers. Okay, so these type of formats are nothing but format number 1 and format number 2. See, this format number 1 has 1 byte of memory. It means its length is 1 byte. Format 1 instruction needs 1 byte of memory. Okay, so it means that how many bits it wants? 8 bits it wants. So that 8 bits are reserved only for one field. That field is opcode field, that is OP field. Okay, best example is here I have written R sub is one instruction. R sub is one instruction that meaning of this R sub is return to subroutine or return from subroutine. Okay, return to subroutine or return from subroutine. So this instruction contains only 8 bits. Those 8 bits are reserved for opcode. So only now we have to find out opcode of this R sub. So we will learn how to find out this opcode of R sub in next classes. Don't worry. The opcode of R sub is 4C. Okay, this 4C, this 4 is indicated in the form of binary, and this C is hexadecimal value it is actually, and this C is also converted to binary, and total 4 plus 4, total 8 bits are filled now. This 8 bits are nothing but opcode. Here we have seen here. So we have listed here binary numbers from 0 to around 15. So with the 4 bits, 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. For these all 16 numbers we have written binary numbers with the 4 bits here, and 10 is called as A in hexadecimal, 11 is called as B in hexadecimal, and the C is 12, and D is nothing but 13, and E is 14, and F is 15. So here C is nothing but 12 binary value is 1100. That C only I have written here. So this is how we have to write the format number 1 instructions. Format number this R sub instruction is in which format now? It is in format number 1. Like R sub, there may be any other instructions also may be present in SIC XC. This is just one example. So in front of this R sub instruction, here in this place, after space, here in this place we have not written any register, we have not written any variable or operand which is using a memory. So this format number 1 is not using a memory at all. Okay, only just instruction is there, that is R sub instruction. Let us move to format number 2. The instructions may be in this formats also. First is 8 bits are reserved for opcode, and the next 4 bits are for register 1, and next 4 bits are for register 2. The best example is here I have written COMPR. Just focus here, it is not only COMP, it is COMPR. It means that it is not only comparing, it is comparing registers. So it is compare the register instructions, compare registers. So if R is not present there, then it will be COMP, compare register, compare instruction, which we can use in SIC also, because it is available in SIC machine also. But here this is not, here this is not a COMP, it is a COMPR. It means here compare the registers. Which register it wants to compare? It wants to compare these two registers, register A and register S. If you observe here, A is accumulator register. A is accumulator register which is present in SIC machine, but this register we are using in SIC XC code also. It means that SIC XC has AXL PCSW. Also it contains the registers B, S, T and F registers. F registers. So total SIC XC has 9 registers. In that one, first register is A, and in this instruction second register is S instruction, so which is present in SIC XC. So here only you can see and you can understand that SIC XC contains total 9 registers. Okay, then what is the meaning of this instruction? It compares the contents of A registers with B registers. So here note I have written here, see, it is not a COMP, it is a COMPR. It means that it compares the registers. So COMP is on SIC machine. Okay, COMPR is available only in SIC XC machine. Okay. See here we have to find out the opcode of this instruction COMPR, and here that opcode is A0. A is hexadecimal value and its equivalent binary number in 4 bits is 1010, and 0 is 0. So here we are representing this 0 with 4 bits. So total 8 bits of opcode we have written for compare register instruction. Then next 4 bits are reserved for register 1. Small letter r is nothing but register 1. The first register is A, so that A register number is 0, because accumulator register number is 0. So this 0 is represented as 4 bits here. And when we were studying these registers in SIC as well as in SIC XC, in second column we have studied the numbers of those registers. So the number of register A is 0 and the number of register S is 4. So this 4 is indicated in binary as 0100. So this is how we have got now object code. So what is that? Upcode of COMPR instruction is A0 and the number of register A is 0 and the number of register S is 4. So this is object code. So this generating object code itself is a very challenging task. So and why we need this object code I will explain you later. So we have to now onwards we have to start to learn to generate this object code or to find out this object code. Okay, this 0 and 4 are register numbers of A and S respectively. So let us move to format number 3. This format number 3 length is 3 bytes. It means that 24 bits or else one word. So total the length of this format number 3 instructions are 24 bits. In that first 6 bits are represented for opcode or reserved for opcode and the next 6 bits are flag bits. Those flag bits are NIXBPE. Remember, you should not interchange these sequence or order. So these flag bits should be written in this sequence only. N after I, after X, after that B, after that P, after that E. So we cannot interchange these sequence or order. So these all NIXBPE are flag bits. So these all flag bits will take 1111 bit, and next last remaining 12 bits will be reserved for displacement. So I will tell you the meanings of these words or terms: displacement, target address and effective address. These all things after the completion of this topic, don't worry about it. So 6 bits are for opcode and next 6 bits for flag bits and last 12 bits for displacements. So total format number 3 is of length 24 bits. So this LDA hash 3 is there. So this instruction LDA we have to find out opcode. The opcode of this LDA is 00. So first 0 will be represented in a binary 0000 in 4 bits and second 0 is also represented here. In that one only first two zeros we have to use because only 6 bits are available for us. Only first two zeros we have to use here. Next NIXBPE. So n value we have put it as 0 and x value we have I value we have put it as 1 and x value is 0, b value is also 0, p value is also 0, e value is also 0. So how we are writing these values 0 1 0 1 0 1 for these flag bits I will explain you in next class. Don't worry about it. This is just one example I am showing here. So how exactly we have to write these values I will show you in the next class. Then last displacement also how we have written these 003, that is also I will tell you in the next class. Don't worry. So this 0 is represented as 4 bits binary number and this 0 is also represented in binary with 4 bits and this 3 is also represented in its equivalent binary numbers 0011. So how we are getting these all values and this object code I will explain you in next class. Don't worry. So next let us move to format number 4. So instructions in SICXE may be in this format also. This format number 4 takes 4 bytes of memory. Format number 1 takes 1 byte, format number 2 takes 2 bytes, format number 3 takes 3 bytes. Similarly format number 4 takes 4 bytes. So this 4 bytes is nothing but 24 plus 8, 24 plus 4 30 34 bits. See, 34 bits length is here. 6 plus 6 12, 12 plus 20, that is 32. Yes, total 4 bits means 4 bytes means 8 into 4, 8 4 32. 32, sorry I told you 34 by mistake. Actually there are 32 bits will be there because 1 byte is equal to 8 bits, and here there are 4 bytes are there in this format number 4. So 4 into 8, 8 fours are, or 4 eights are 32. So total 32 bits will be there in the format number 4. The first 6 bits are for opcode, and next 6 bits are for flag bits, and last remaining 20 bits are for address field. If you can observe here, address field is of length 20 bits, but in SIC machine address field was only 15 bits. Okay, and even in format number 2 also, this displacement field was only of 12 bits. Okay, so but now we are seeing here 20 bits of address field. You just try to differentiate between this one and this one, don't get confusion. This is a displacement, which is also similar to our memory or address, and here it is exclusively and clearly it is address. Here displacement is of length 12 bits, and here address is of length 20 bits. So here in SICXC there are total 4 instruction formats are there. So first instruction format is of only 8 bits, that is 8 bits are reserved for opcode, and in format number 2 it takes 2 bytes. In that first 8 bits are opcode, and the next 4 bits are for register 1, and last 4 bits for register 2. So total here 2 bytes are there. 2 bytes are nothing but 16 bits are present here. Okay, and then format number 3 is of length 3 bytes, and first 6 bits for opcode, next 6 bits for flag bits, and last 12 bits for displacement. So total there are 24 bits are there. And in format number 4 there are 4 bytes are there. 4 bytes are nothing but 32 bits. So first 6 bits are for opcode, next 6 bits for flag bits, and last 20 bits are for address field. These are the 4 instructions formats we have in SIC XC machine. And when we have to use format number 4, so we have to use only format number 4 only when this instruction is prefixed with plus symbol. So then only we have to use format number 4. This is just one hint or one clue I am giving you in this stage, just to remember. So only when the instruction is prefixed with plus symbol, at that time only we have to use this format number 4, which is very rare, okay, in our program. Plus JSub opcode we have to write here, and since there are only 6 bits are there, from that 4 and something is there, the opcode of JSub, we will find out it later. The 4 is represented into binary number with 4 bits, that is 0 1 0 0, and next 1 0 is there. Only 2 bits of next digit or next number we have taken here. Then remaining 2 bits we can eliminate, and then start writing these values of flag bits NIX BPE. So why it is N value is 1, I value is 1, this X BP values are 0, and E values are 1. These all things I will clearly explain you in the next class. Then this 20 bits of address is there. Then 20 bits of address directly we can take it as address from the instruction. And since if it is address is 1036, for example, that complete address we are representing it into binary numbers with 4 bits, and remaining 4 bits are blank or empty here. Those remaining bits will be filled with 0. So by this example you understood that we have to start to fill these 20 bits of address field from right to left. First start to fill these 4 bits for this 6, and next 4 bits for this 3, and next 4 bits for this 0, and next 4 bits for this 1. Now remaining again 4 bits are blank now, or available now. Those 4 bits just we can put them as 0. So this is how we have to find out object code. Okay, clearly once again in detail I will explain you, don't worry. So that next is the fifth point is addressing modes. So in SIC machine there were only two addressing modes. One is direct addressing mode and second one was indexed addressing mode. So direct addressing mode was indicated by a flag bit small letter X value 0, and indexed addressing mode was again indicated by the flag bit small letter X value 1. But here there are more than two addressing modes are there in SIC XC because of the increase of memory. Okay. So two relative addressing modes are available for this instruction of format number 3, particularly in SIC XC. In SIC XC for format number 3, there are two relative addressing modes are there. Remember this word, relative addressing mode. Okay. So almost all instructions in SICXC will be in format number 3 only. So very small number of instructions will be either in a format number 1 or else format number 2 or else format number 4. So but almost all maximum number of instructions will be in format number 3. For those format number 3 instructions, we have to use these relative addressing modes. So two relative addressing modes are available for us for this format number 3 in SIC XC. So those relative addressing modes are base relative addressing mode and program counter relative addressing mode. The first relative addressing mode is base relative addressing mode. Second relative addressing mode is program counter relative addressing mode. So next addressing modes are direct addressing mode, indexed addressing mode, immediate addressing mode, then indirect addressing mode, then last one is simple addressing mode. So total there are 7 addressing modes are there in SIC XC. So this base relative addressing mode, how to find out or how to indicate it. So how to indicate it? By using small letter flag bit B to 1 and by using 0 value for a flag bit small letter P. If B is 1 and P is 0, then it is in base relative addressing mode. It means that that instruction is using base relative addressing. So as its name itself is base, so here B, small b will be 1 and small p will be 0, and target address calculation formula is target address is equal to displacement plus content of the register B or content of the register B plus displacement. So always this displacement value will be in between 0 and 4095. So this formula we have to remember to solve the problem in the next classes. And program counter relative, its name itself is a program counter. So program P, so this B value will be 0 now and P value will be 1, and target value target address value will be PC plus displacement, that is nothing but displacement plus content of the register PC, program counter register, what we have already studied in SIC machine. The content of that register plus displacement will be the target address, and this displacement will be usually in between the values from minus 2048 to plus 2047. And next addressing mode is the direct addressing mode. This direct addressing mode was indicated in SIC with the X bit as 0, but here this direct addressing mode is indicated as a B is equal to 0 as well as P is equal to 0. Then a displacement value will be directly target address, or target address value will be directly displacement when we are using format number 3. If we are using format number 4, then target address will be directly that address field or value of that address field. So usually when we use this format number 4, whenever the instruction is prefixed with plus symbol, so at that time directly we can take that address as a target address. If you are using or if the instruction is in format number 3, then that directly displacement value we can take it as target address. So because of this, directly taking the values of displacement and directly taking the values of address as a target address, so this addressing mode is named as direct addressing mode. So first addressing mode is a relative addressing mode, that is a base relative addressing mode. Second is also relative addressing mode, that is a program counter relative addressing mode. Then direct addressing mode. Then fourth addressing mode is indexed addressing mode. Indexed addressing mode is indicated by the value of flag bit x equal to 1. If x value is equal to 1, then that addressing mode is indexed addressing mode. So same thing we have used in SIC machine also. In SIC machine also, if x value is 1, then we called it as indexed addressing mode. Then target address will be displacement plus content of the register x. X is nothing but in first SIC machine we have studied the registers A, X, L, PC and SW. There we studied this X register. That X register is called as index register, and it is used for addressing purpose. The same content of that register will be added with the displacement to get the target address. And then next addressing mode is immediate addressing mode. And here how to identify it is in immediate, if an instruction is in immediate addressing mode, if that instruction is prefixed with hash symbol, then that instruction is in immediate addressing mode, or that instruction can be converted into low level language or machine level language with the help of immediate addressing mode. And how to represent or how to indicate that in immediate addressing mode. So as its name itself is immediate I, so I value will be 1 here and n value will be 0. So n is 0 and I value is 1. If these two values are in these flag bits, then this addressing mode is immediate addressing mode. And operand value, whatever the operand value is there in our instruction, that operand value will be directly taken as a target address. So since I am talking and I am speaking operand value only, we are going to take it as a target address. There will be no any memory reference or there will be no any memory usage. Okay, then next addressing mode is indirect addressing mode. Indirect addressing mode, how to identify it? So if that instruction is begin or prefixed with at symbol, at the rate symbol, then that instruction can be solved with indirect addressing mode. And these indirect, so n value will be 1 and I value will be 0. The word at the location given by the target address is fetched, and that value contained in this word is taken as a operand value. So this is how we have to find out the target address for this indirect. So whatever the word is there, word at the location given by the word target address is fetched. Here word is nothing but 3 consecutive bytes. That word at the location given by the target address is fetched, and the value contained in this word or bytes of 3 bytes is taken as a operand value. And last is simple addressing mode. Simple addressing mode, in simple addressing mode n as well as I value will be 0, or else both n and I values will be 1. If both values of I and n are 0, then it is a simple addressing mode. If both I and n values are 1, again it is a simple addressing mode. If n value is 0 and I value is 1, then it is immediate addressing mode. And if n value is 1 but I value is 0, then it is indirect addressing mode. Okay, in simple addressing mode, target address calculation is like this. Target address is equal to location of operand, that is address only, directly we can take it as target address. And base relative addressing mode, here one example is given here for base relative addressing mode. The instruction is stx length. So here first we have to find out opcode of stx and we have to fill these fields, and these bits also we have to fill with NIX BPE. With the help of this NIX BPE, we can easily identify which addressing mode here we are using. Here N as well as I values will be 1 for almost all instructions, but even though N and I values are 1, we cannot say that it is a simple addressing mode. So it is in a base relative addressing mode, because maybe in next flag bits the B value will be 1 and P value will be 0. You can observe here B value is 1 and P value is 0. So this instruction STX instruction is using base relative addressing mode, and X value is 0 here. So if X value is 0, it is not indexed addressing mode also. So next E value is 0. E value is 0. Why E value is 0? E flag bit indicates that which format we are using for this instruction. So if we are using format number 3 for this instruction, then E value will be 0. If we are using format number 4 for any instruction, at that time we have to use this E value as 1. Okay, this is how we have to fill the values of these flag bits NIX BPE. Next we have to find out the displacement with the formula given here. So since it is base relative addressing mode, so we have to find out a target address. That target address formula is B plus displacement, but in our format 3, this 12 bits of displacement we have to fill here. We don't want target address value, we want displacement value. So if you want displacement value, then the equation will be displacement is equal to target address minus base register, that is B. Okay, so that base register on after that we will get that target address as 0 0 0. So these all zeros will be filled with this 12 bits, and this NIX BP already I told you how to fill, and this is opcode how to find out and how to fill this one. Finally, whatever the code we will get here, whatever the number we will get here, this is called as object code. Okay, so here length is there, effective address length is assumed as address of length is 0033. The address of this length is or operand length is treated as or taken as 0033, and effective address or target address formula is displacement plus B, but I want displacement value. First substitute the value of effective address, that is 0033 equal to displacement I have to calculate, and here I have assumed that the content of register B is also 0033. So here displacement value will be what here displacement value will be EA minus content of register B. So EA is also 0033 minus B is also 0033, and make a hexadecimal subtraction here, don't do normal subtraction. So we have to make them as hexadecimal subtraction with the calculator, then we will get 0000. It means that displacement will be filled with 3 zeros. So each zero will be filled with 4 bits of zeros, binary zeros, 4 bits of binary zeros, and this is also filled with 4 bits of binary zeros. The content of address 0033 is loaded to the index register X here. It means that here store, this instruction is telling that to store the content of length into X register. So store and load instructions are there. Load instruction always moves the data from memory to load instruction always moves the data from register to memory, but here it is a store ST. Store register store instruction always moves the data from memory to register. So because of that only the content of address or memory 0033 is loaded or stored to the index register X. Remember the data movement in load and store register. The data movement in load register load instruction is from register to memory, but in store instruction the data movement is from memory to register. So next come to program counter relative addressing example is here, that is NIX BPE. You can observe here NI are again 0, X is also 0, but B is 0 and P is 1 here. And again, since we are using format number 3, E is also 0. So this is the main important thing here. We have to learn how to find out or how to fill these flag bits NIX BPE. Okay, so next we will see direct addressing mode. Direct addressing mode example is also here we have given, that is NI11 direct addressing mode. So again, X is also 0, B is also 0, P is also 0, as it is as that instruction is using direct addressing mode. So both B as well as P are 0 and E is also 0, since that instruction LDA is in third format. Okay, then indexed addressing mode. So here N and I are again 1 and X is 1 this time because it is indexed addressing mode, and B is also 1 and P is also 1 here. Even though it is in indexed addressing mode, we are going to find out object code with the help of base relative addressing mode here. So because of that only here we are going to take this B value as 1 and P value as 0, and even since it is instruction is in the third format, we have used E value as E value as 0. STCH instruction is in format number 3, STCH buffer comma X. In this instruction only we are using index register X. So just I am giving you hint or clue. Since there is index register capital X, it means that here we have to use a small letter X, that is flag bit, to indicate that is in indexed addressing mode. Okay, now X value is 1. So this is how we have to find out the values of NIX flag bits. Next, immediate addressing is there. In immediate, I already told I value will be 1 and N value will be 0, and instruction is containing one operand. That operand, if it is prefixing with hash symbol, then obviously that instruction is using immediate addressing mode. So I is 1 and N is 0, and X is also 0, B is also 0, P is also 0, and E is also 0. Then indirect addressing, don't get confusion with immediate, indexed and indirect. So indirect it is, so N is 1 and I is 0, X is also 0, B is also 0, P is 1 and E is 0. So it means that here this equation, this instruction J instruction is solved with program counter relative addressing mode. So P is 1 here. J is nothing but a jump instruction. So and again here this operand return address, this operand is prefixed with @ symbol. So this instruction is using indirect addressing mode. And next last one is simple addressing. If both values of N and I are either 0 or 1, then that addressing mode is simple addressing mode. Then that target address is taken as a location of that operand directly. So this is called as simple addressing. See, indexed or indexing cannot be used with immediate or indirect addressing modes. It means that in immediate and indirect addressing mode, indexed cannot be used. It means that in immediate and indirect addressing mode, here we are not using X value, we are keeping this X value is always 0. In immediate addressing also we have used X value as 0, but in this indexed addressing mode we are using that X value as 1. Okay, then next topic is flag bits and flag bits in format number 3 and 4. Just for your understanding purpose, once again I have written here, that is E, it is used to distinguish between format number 3 and 4. if E is 0, it means that instruction is using format number 3, and if E is 1, then that instruction is using format number 4. And B value, if it is used to indicate that base relative addressing mode, whether the instruction is using a base relative addressing mode or what. If B value is 1 and P value is 0, it means that it is base relative addressing mode. And P, small letter P, it is used to indicate program counter addressing mode. If B is 0 and P is 1, then it is in a program counter relative addressing mode. If both of them are 0, that is B is also 0 and P is also 0, then displacement field from format number 3 instruction is taken as the target address. So it means that the addressing mode is a direct addressing mode. Okay, so then X value, X flag bit, if the index flag X is set to 1, the form or the term capital X, or that is content of register X, is added in the target address, in the target address calculation. Then I and N, so if both I and N are 0 or 1, then it is a simple addressing mode. If I is 1 and N is 0, then it is a immediate addressing, and operand will be prefixed with hash symbol. Then if N is 1 and I is 0, then it is indirect addressing mode, and that operand will be prefixed with @ symbol. If both of them are 0 or 1, then it is a simple addressing. Note that in SIC XC machine, instructions instructions, if both N and I are set to 1, then addressing mode is not immediate, or it is not indirect. So these are all the observations you have to do. And if both N and I are set to 0, then bits B, P and E are considered as a part of address field of this instruction, instead of flag bits used to indicate addressing modes. Okay, then next part is sixth part is instruction set. What are the instructions are available in SIC XC machine? SIC XC provides all instructions available on SIC. In addition to these instructions, it is also providing us some following instructions. In SIC, I think you remember, we have some arithmetic instructions, that is add, addition, subtraction SUB, and multiplication MUL, and division DIV. In addition to these instructions, there were many other instructions like compare instructions, COMP, and some instructions to test the device like TD, and if the device is ready, then you use RD, read data, or WD, write data instructions. Like this, some other instructions were there to load and store the memory or registers. That is nothing but for data movement operations. We have used load instruction and store instructions there, that is LD and ST instructions. Like this, some enough instructions were there in SIC. Similarly, in addition to those instructions, SIC XC also has some extra or additional instructions. Those instructions are again to load and store the new registers. See here, so in SIC we could not store, or we could not deal with registers, two registers. One register could deal with memory, and memory could deal with register. But here in SIC XC, it is possible to deal with two registers at a time. So here we can call these registers as or instructions as register instructions, or register to register instructions, to load and store these new registers. Again, here we are going to use load and store registers, LDB, STB, etc. New registers means here we have 4 new registers in SIC XC, BS, TF. To load those registers, we have these instructions: LDB, STB, LDS, STS, LDF, STF, like this. For new registers we have load and store register instructions. Second type of instructions what we can use in SICXC are to perform floating point arithmetic operations like add F, subtract F, multiplication F, division F. We can observe here instruction is ADDF. It is not only ADD, and it is not only SUB, it is SUBF. It is not only MUL, it is MULF. It is not only DIV, it is DIVF. So these all arithmetic operations we could perform in SIC also, but with accumulator register capital A. But those arithmetic operations were for normal data like integers and negative integers. But here we are going to store the floating point values also in SICXA. We can perform arithmetic operators with arithmetic operations with these floating point values. So the instructions will be obviously ADDF, SUBF, MULF, DIVF. And third type of or set of instructions are to take the operands from registers. It means that data is moving from register to memory. So that is register move, that is RMO. Then to perform register to register arithmetic operations, ADDR, SUBR, MULR, DIVR. So these are also not ordinary arithmetic instructions like add, subtract, multiplication, division. These are addition of registers, subtraction of registers, multiplication of registers, and division of registers. So these type of instructions are called as register to register arithmetic operations and or instructions. And next type of instructions are to generate an interrupt or disturbance during the communication with OS. That is nothing but SVC instruction, that is supervisor call. Already in OS subject you have studied how to generate interrupt to this OS. Okay, the instruction SVC, that is supervisor call, will be used to do this interrupt. Okay, next last part of this SICXC is input and output operations. SICXC provides all instructions which are available in SIC like TD, RD and WD to perform input output operations. In addition to these three instructions, this SICXC machine is using some input output channels to perform this input output operations when this CPU is executing other instructions. And input output channels help this CPU by reducing the workload of CPU. And because CPU can focus or concentrate on main functions or operations instead of bothering about these input output operations, because input output operations are handled by this input output channels. Okay, and input output channels and CPU perform simultaneously, thereby increasing the efficiency of the system also. And instructions like SIO, TIO and HIO are used to start input output operation, test input output operation, and halt the input output operation of these input output channels. So totally here many number of instructions we can use to perform input output operations on SICXC machine. So in addition to this TD, RD and WD, it is also using SIO, TIO and HIO to control this input output channels. And input output channels will perform input output operations. So somewhat some load or workload of a CPU will be reduced. Since the CPU as well as input output channels work simultaneously, we can increase the efficiency of system in SICXC. So this is about SICXC machine architecture. First concept is memory, then after that registers, and then data format. Third one is data format. Third one is data format. fourth one is instruction formats, and fifth one is addressing modes, and uh, sixth is sixth is instruction set, and seventh is input output. So total 7 concepts we have studied in SIC. XC as a machine architecture or configuration or hardware features. In the next class we will see some programming examples on SIC and SIC XC.